The Airbus H145 is one of the most advanced twin-engine helicopters, widely used for emergency medical services, law enforcement, military operations, corporate transport, and offshore missions. Its Helionix avionics suite, FADEC-controlled engines, and modern rotor system make it highly efficient and safe. Starting up the H145 is a multi-step process, requiring careful attention to system checks, power management, and pilot inputs to ensure a smooth, controlled transition from cold and dark state to flight readiness. The process begins with pre-flight exterior inspections, where the pilot and ground crew visually examine the rotor blades, fenestron tail rotor, fuel tanks, landing gear, and engine inlets for any visible damage, leaks, or foreign objects. This step is essential to identify potential issues before power up. Special attention is given to fluid levels, including hydraulic systems, engine oil, and fuel quantity, ensuring the aircraft is prepared for flight. If the H145 is operating in cold weather conditions, additional precautions are necessary, such as checking for icing, moisture buildup, or external obstructions that may interfere with engine startup or flight performance. Upon entering the cockpit, the battery master switch is turned on, powering up the Helionix avionics suite. The multifunction displays, MFDs, and primary flight display, PFD, provide critical system information, including engine status, fuel levels, rotor speed, and avionics health checks. Pilots review these indicators to verify that no system faults or warnings exist before proceeding. The pre-start checklist is carefully followed, ensuring that all switches, controls, and circuit breakers are in their correct positions. With the aircraft systems verified, the engine startup sequence begins. The H145 is powered by two Safran Ariel 2E turboshaft engines, controlled by a full authority digital engine control (FADEC) system, which optimizes fuel flow, power management, and startup automation. The engine mode selector is set to start, engaging the starter motor, which begins to spool up the turbine. At approximately 15 to 20% N1 compressor speed, FADEC introduces fuel flow and ignition, causing the engine to accelerate toward idle RPM. Engine temperature, oil pressure, and turbine rotation speeds are closely monitored during this phase to prevent hot starts or compressor stalls. Once the first engine stabilizes, the second engine is started using the same automated FADEC-controlled process. As both engines reach operational RPM, the rotor brake is disengaged, allowing the 5-bladed main rotor system to spin up to speed. The fenestron tail rotor, an enclosed fan-in-fin system, automatically adjusts to maintain yaw stability. During startup, pilots confirm that the FADEC has synchronized both engines, ensuring a balanced power output for optimal performance and fuel efficiency. Before takeoff, several flight control and avionics checks are conducted. The cyclic, collective, and anti-torque pedals are moved through their full range to ensure unrestricted movement and proper hydraulic response. The 4-axis autopilot and stability augmentation system, SAS, are tested to confirm they are functioning correctly. The flight management system, FMS, is programmed with the planned route, altitude settings, and waypoints, ensuring navigation accuracy. Additional system checks include radio communications, transponder settings, weather radar, synthetic vision displays, and obstacle awareness systems. The Helionix avionics suite provides real-time data on flight conditions, allowing the pilot to adjust settings before liftoff. The engine power levers are gradually advanced, increasing rotor RPM and engine torque. As the aircraft transitions from idle to hover mode, the pilot carefully adjusts collective input and cyclic pitch, maintaining stability and altitude control. Once in hover flight, additional parameters such as power output, vibration levels, and autopilot stabilization are checked. The H145's high-powered twin-engine setup allows for smooth takeoffs, even in high-altitude or hot weather conditions. When all systems are verified, the pilot increases forward cyclic input, transitioning the aircraft into forward flight. The startup process can vary depending on the mission profile. In emergency medical services, EMS, operations, Rapid startup procedures are often required. Many EMS operators use pre-configured flight plans and standby readiness procedures to minimize launch time. In law enforcement operations, helicopters may be placed in hot standby mode, where engines remain idling to allow for quick response to incidents. Military versions of the H145, such as the H145M, may require stealth startup procedures, using external power sources to reduce infrared signature before takeoff. For offshore missions, where the H145 operates over open water or oil rigs, additional pre-flight weather assessments and navigation checks are required. The aircraft's anti-corrosion coatings, marine-grade avionics, and overwater emergency flotation systems are essential for safe operations. After completing a flight, the shutdown sequence is just as critical as startup. The pilot gradually reduces collective input, lowering the aircraft gently to the ground. The FADEC system automatically reduces engine power, allowing for controlled turbine cool down. The rotor brake is engaged once rotor RPM drops to a safe level, preventing unnecessary spin-down time. Avionics and electrical systems are systematically powered down, and a post-flight inspection is conducted to check for any signs of mechanical wear, fluid leaks, or overheating. The H145's advanced startup automation and pilot-friendly design make it one of the most efficient and reliable multirole helicopters in the industry. Compared to older helicopters, where manual throttle adjustments and complex startup sequences were required, the H145 streamlines the entire process through FADEC control, automated power management, and intuitive cockpit interfaces. Future innovations in the H145 startup process may include eye-assisted avionics, hybrid electric propulsion, and real-time predictive maintenance systems. Airbus Helicopters is actively researching next-generation rotorcraft technologies, which could introduce faster startup cycles, reduced fuel consumption, and improved sustainability. As global demand for high-performance multirole helicopters continues to grow, the H145 remains a leading choice for critical missions worldwide. Whether serving in emergency response, military operations, corporate transport, or offshore logistics, its efficient startup procedures, cutting-edge avionics, and robust safety features ensure that it remains one of the most advanced and trusted helicopters in the industry. For YouTube videos demonstrating the H145 startup process, high-quality visuals, cockpit footage, step-by-step explanations, and real-world use cases can enhance viewer engagement. Combining pilot commentary, graphical overlays, and in-flight perspectives will help create an immersive and informative experience for audiences interested in helicopter operations and aviation technology. The Airbus H145 is a multi-mission, twin-engine helicopter designed for efficiency, safety, and versatility. It serves across medical evacuations, law enforcement, military operations, corporate transport, and offshore logistics. One of the key strengths of the H145 is its advanced startup procedure, designed to reduce pilot workload while ensuring operational safety. The Helionix Avionics Suite, full authority digital engine control, FADEC system, and streamlined automation work together to make the engine start and flight preparation process more intuitive compared to traditional helicopters. Expanding on the startup process, a in-depth explanation. Before beginning the startup sequence, a thorough exterior inspection is performed. Pilots and ground crews check main rotor blades for cracks, deformations, or signs of fatigue. Fenestrawn tail rotor for any obstructions or debris that may have accumulated in confined environments. Engine inlets and exhaust outlets for foreign object debris. FUD, hydraulic systems and fuel lines for leaks or abnormalities. Landing gear integrity and tire pressure. For wheeled variants, the pre-flight exterior check is especially crucial in extreme weather conditions, such as cold weather operations, where icing and snow accumulation could impact engine startup or rotor aerodynamics. Hot and high-altitude environments, where thinner air requires more precise engine power adjustments. Marine and offshore operations, where salt corrosion prevention measures must be taken. Cockpit preparation and power-up sequence. Upon entering the H145 cockpit, the battery master switch is engaged, activating the aircraft's avionics, flight displays, and electronic systems. The Helionix flight deck immediately runs a self-diagnostic check, displaying the status of navigation and communication systems, FADEC-controlled engine monitoring, rotor speed and hydraulic pressure, flight management system, FMS, readiness. The flight control panel is reviewed to ensure that the cyclic and collective controls move freely with no hydraulic pressure loss. Pedals are functioning correctly for yaw control via the fenestron tail rotor. The autopilot and stability augmentation system, SAS, are online. Once the systems are verified, ground communication is established. Air traffic control, ATC, clearance is obtained in controlled airspace environments, while in emergency response or tactical operations, quick clearances are coordinated through pre-approved flight plans or command center communications. Engine startup. A dual-engine synchronization via FADEC. The H145's twin Safran Ariel 2E turboshaft engines are designed for automated power control via FADEC, allowing a precise and efficient startup sequence. 1. First engine spool-up begins with the pilot setting the engine mode selector to start. 2. The starter motor engages, increasing N1 compressor speed to around 15 to 20%. 3. FADEC automatically introduces fuel injection and ignition, ensuring a controlled and efficient light-off process. 4. The engine stabilizes at idle speed, with exhaust gas temperature, EGT, oil pressure, and turbine RPM monitored closely. 5. The second engine undergoes the same process, ensuring balanced power distribution for smooth rotor engagement. As both engines reach operational RPM, the rotor brake is disengaged, allowing the 5-bladed main rotor to reach full rotation speed. The fenestron tail rotor automatically compensates for yaw drift, maintaining stable hover readiness. Pre-takeoff system checks and mission-specific adjustments. With both engines running, final system checks ensure all flight parameters are set. Hydraulic system pressures are within safe limits. Flight instruments and displays show correct altitude, speed, and heading data. Autopilot functions are tested to verify stability. Augmentation system, SAS, integrity, weight and balance are confirmed, especially in EMS on military transport missions. Depending on the mission profile, additional pre-takeoff adjustments may be required. EMS, emergency medical services, operations, quick power and standby mode for immediate response times. Military deployments, stealth startup procedures utilizing external ground power units to reduce thermal infrared signature. Law enforcement patrols, hot standby configurations for rapid pursuit deployment. Offshore transport, extra weather and wind assessments to ensure safe takeoff from oil platforms or maritime vessels. Takeoff and transition to flight. Upon clearance, the pilot gradually raises the collective, increasing engine torque and rotor RPM. The H145's digital engine controls adjust power output automatically for smooth liftoff. Hover checks are performed to ensure no uncommanded drifts or instability. Autopilot stabilization is correctly engaged. Yaw control via the fenestron tail rotor is balanced. Once stable in a hover, forward cyclic input is applied, allowing the helicopter to transition into forward flight. The Helionix avionics suite provides real-time flight data, enhancing pilot awareness. Emergency scenarios during startup and takeoff. While the H145 is designed for reliability and redundancy, pilots must be prepared for emergency conditions. Hot start prevention. FADEC shuts down the engine automatically if temperatures exceed safe limits. Rotor brake malfunction. Secondary procedures allow for manual disengagement or emergency shutdown. FADEC failure. A manual override enables pilots to control engine throttle manually. Loss of hydraulic power. The H145 features backup hydraulic pumps and emergency handling techniques. Post-flight shutdown and system cool down. After completing a mission, the shutdown process ensures safe engine and rotor cooling. 1. The collective is gradually lowered, reducing engine power and rotor RPM. 2. The FADEC system enters a control cool-down cycle, stabilizing turbine temperature and fuel flow. 3. The rotor brake is engaged once safe speeds are reached. 4. Avionics and power systems are systematically shut down. 5. A final walk-around inspection is performed to detect any potential issues before the next flight cycle. Future developments in H145 startup technology. Airbus is continuously developing new advancements in rotorcraft technology, including hybrid electric propulsion systems to reduce fuel consumption and environmental impact, AI-assisted startup diagnostics to predict maintenance needs before failures occur, enhanced automation allowing for semi-autonomous helicopter operations in high-risk environments. The H145 remains one of the most trusted and advanced helicopters, and its startup procedures are a testament to its efficiency, reliability, and cutting-edge design. Whether in high-stakes rescue missions, law enforcement, military operations, or offshore transport, the startup process of the Airbus H145 ensures mission success. For YouTube videos, providing step-by-step cockpit footage, graphical overlays, and real-world pilot commentary will enhance viewer engagement, making aviation technology accessible and exciting for audiences worldwide. The Airbus H145 remains one of the most advanced twin-engine helicopters in its class, primarily due to its Helionix avionics suite, FADEC-controlled engines, and high-performance rotor system. The startup process, while streamlined and highly automated compared to older helicopters, still requires strict adherence to procedures to ensure operational safety, mission readiness, and optimal performance. 1. The role of automation in H145 startup. The introduction of automation in the H145 startup sequence has transformed the way pilots interact with the aircraft. The Helionix avionics suite plays a crucial role in monitoring engine parameters, power distribution, and flight readiness. Unlike older helicopters, where manual throttle adjustments and extensive startup checklists were required, the H145 simplifies this through FADEC, Full Authority Digital Engine Control System. Ensures precise fuel delivery, startup sequence monitoring, and automatic engine shutdown in case of irregularities. Avionics self-testing procedures. When the battery master switch is engaged, the system performs an automatic diagnostic scan, identifying any potential faults before startup begins. Electronic Flight Instrument System, EFIS, integration. Displays critical startup data, allowing pilots to verify that all systems are functioning correctly. Automatic rotor synchronization. The 5-bladed main rotor system and Fenestron tail rotor are automatically synchronized during startup to ensure smooth power transfer. These features significantly reduce pilot workload, allowing for faster and safer startup times, especially in high-pressure mission environments like emergency medical services, EMS, law enforcement, and military operations. 2. Detailed walkthrough of the H145 cockpit and startup controls. Inside the cockpit, the H145 features an intuitive layout, ensuring that all critical startup functions are easily accessible. The key components involved in startup include battery master switch. Powers up the aircraft's electrical systems and avionics. Engine control panel. Houses the FADEC-controlled startup switches for both engines. Multifunction displays, MFDs, provide real-time system status, including engine temperature, fuel levels, and electrical power readings. Cyclic and collective controls. Checked before startup to ensure smooth movement and correct hydraulic response. Pedal controls. Adjust the Fenestron tail rotor, ensuring yaw stability during startup. Each of these controls plays a vital role in ensuring a seamless startup sequence. The ergonomic design of the H145 cockpit allows pilots to quickly access all necessary controls, ensuring a smooth and efficient power-up sequence. 3. Cold weather startup procedures. When operating in extreme cold environments, additional startup precautions are necessary. Preheating engines and sub-zero temperatures. Engine oil thickens, making startup more challenging. The H145 is equipped with an engine preheating system to ensure proper lubrication. Battery warm-up. Cold temperatures reduce battery efficiency, so external power sources are sometimes required for startup. Icing prevention. The main rotor blades and fenestron tail rotor are checked for ice buildup, as ice can significantly disrupt airflow and rotor efficiency. The FADEC system automatically adjusts fuel flow and power output in cold conditions to compensate for a lower air density, ensuring a smooth engine ignition. 4. High altitude and hot weather startup considerations. In high altitude or hot weather environments, air density is lower, which affects engine performance. During startup, the FADEC system automatically adjusts fuel-air mixture to compensate for lower oxygen levels. Rotor engagement is carefully monitored, as hot weather can increase engine workload and risk of overheating. The aircraft weight and balance are recalculated, ensuring that takeoff power requirements are met. These environmental adaptations highlight the H145's versatility, allowing it to operate in diverse and challenging conditions. 5. Mission-specific startup adjustments. The startup process varies depending on the mission type. Emergency medical services, EMS, operations require rapid startup, often in under 2 minutes, to minimize response time. Pilots use pre-configured checklists and standby power settings to reduce startup delays. Law enforcement operations. Some police aviation units keep helicopters in a hot standby mode, where engines are idling, allowing for instant takeoff when needed. Military and Special Forces deployments. The H145M variant features low-noise startup capabilities and optional external power sources for stealth operations. These mission-specific adjustments optimize startup efficiency depending on operational demands. 6. Advanced safety features in the startup process. The H145 is equipped with multiple safety layers, ensuring that startup anomalies do not lead to mission failure. These include automatic hot start prevention. If engine temperature exceeds safe limits, FADEC automatically shuts down the startup sequence to prevent damage. Redundant hydraulic and electrical systems. Ensures continuous power supply and hydraulic pressure stability even if one system fails. Emergency engine shutdown procedures. Pilots can manually override a FADEC system and shut down engines if an emergency arises. These features make the H145 one of the safest helicopters in its class, ensuring reliable startup under all conditions. 7. Post-startup system integration and takeoff readiness. Once startup is complete, the final checks before takeoff include hover power check. Ensures that engine power output is balanced and stable. Autopilot system activation. The 4-axis autopilot and SAS system are engaged, allowing for stabilized flight control. Weight and balance verification. Ensures that the aircraft is properly loaded for its intended mission. After these checks, the pilot transitions from idle to hover flight, making final yaw adjustments using the fenestron tail rotor. The aircraft is then ready for forward flight, marking the successful completion of the startup process. 8. Future innovations in helicopter startup technology. Looking ahead, Airbus is exploring several innovations to make helicopter startup even more automated and efficient. AI-powered pre-flight diagnostics. Future iterations of the H145 may feature predictive maintenance AI, allowing pilots to identify system issues before they arise. Hybrid electric propulsion. Developing hybrid-powered helicopters that reduce fuel consumption and emissions while maintaining high-performance capabilities. Remote startup capabilities. Some military applications may involve remote-controlled startup and pre-flight checks, allowing for unmanned deployment in high-risk zones. These advancements will redefine helicopter operations, making startup processes even faster, safer, and more intuitive. Conclusion. The Airbus H145 startup process is a highly optimized, automated, and safety-driven procedure, making it one of the most advanced helicopter startup sequences in the world. With cutting-edge avionics, FADEC-controlled engines, and adaptive mission configurations, the H145 remains a benchmark for modern rotary-wing aviation. For YouTube video content, incorporating detailed cockpit footage, pilot commentary, and in-depth animations will enhance viewer engagement, providing an educational and immersive experience for aviation enthusiasts worldwide. The Airbus H145 stands as one of the most advanced twin-engine helicopters, integrating cutting-edge avionics, automation, and digital engine control to create a streamlined and efficient startup sequence. Whether used in emergency medical services, EMS, law enforcement, military operations, corporate transport, or offshore logistics, the H145 is designed for rapid deployment, safety, and reliability. Expanding on the previous discussion of startup procedures, this section will explore technical specifications, operational nuances, troubleshooting protocols, and real-world adaptations of the H145 startup sequence. 1. The evolution of helicopter startup automation. Helicopter startups have traditionally been manual, complex, and time-consuming, requiring precise throttle control, hydraulic adjustments, and multiple system checks before flight. The H145 revolutionizes this process with FADEC-controlled engine management, eliminates the need for manual throttle adjustments, optimizing fuel flow and power output. H145 avionics suite provides a real-time digital cockpit interface that monitors and adjusts startup parameters dynamically. Electronic Flight Instrument System, EFIS, displays all engine, hydraulic, and navigation data in an intuitive digital layout. These automation advancements significantly reduce pilot workload, enabling faster and more efficient startup sequences compared to older helicopter models. 2. External pre-flight preparations and checks. Pre-startup walk-around inspection. Before entering the cockpit, a comprehensive external check ensures the aircraft is airworthy. The pilot and ground crew inspect main rotor blades, checking for cracks, erosion, or deformation. Fenestrone tail rotor, ensuring no debris or obstruction affects yaw control. Landing gear integrity, verifying tire pressure, four-wheeled variants, and shock absorber status. Engine intakes and exhausts, clearing any foreign object debris. FUD, hydraulic and fuel systems, checking for leaks or pressure anomalies. Special considerations apply to extreme weather conditions. Cold weather operations, ensure no ice accumulation on rotors or control surfaces. Hot weather operations, monitor fuel expansion risks and engine cooling efficiency. 3. Cockpit entry and system power-up. Upon entering the H145 cockpit, pilots initiate the battery master switch, bringing the aircraft's avionics, navigation systems, and communication interfaces online. Avionics self-diagnostics. The H145 suite performs an automated system check, flagging any abnormalities. Flight control surface check. The cyclic, collective, and pedals are tested for smooth movement. Communication system activation, ground crew and ATC clearance are confirmed. This phase ensures that all electronic systems are fully operational before engine ignition begins. 4. Dual engine startup sequence. The H145 is powered by twin Safran Ariel 2E turboshaft engines, providing enhanced redundancy in power efficiency. The FADEC-controlled startup sequence proceeds as follows. 1. Engine mode selector to start, initiates automatic engine spool-up. 2. Starter motor activation, increases on-one compressor speed to 15 to 20%. 3. FADEC-controlled fuel injection, precisely regulates fuel introduction to prevent hot starts. 4. Engine stabilization at idle RPM, rotor brake remains engaged until both engines are at operational idle speed. FADEC continuously monitors and adjusts fuel flow, temperature, and power output, ensuring an efficient and stable engine startup process. 5. Hydraulic, rotor, and autopilot system engagement. Once both engines reach idle speed, rotor brake disengagement, the 5-bladed main rotor slowly begins rotating. Hydraulic system pressure verification, ensures flight control responsiveness. Autopilot and SAS activation, the 4-axis autopilot stabilizes yaw, pitch, and roll for optimized flight control. This phase ensures smooth rotor engagement and full hydraulic control before takeoff. 6. Mission-specific startup configurations. The H145 startup sequence can be adjusted based on the mission type, emergency medical services, EMS, adaptations. Standby power mode, keeps critical systems online for rapid takeoff, pre-programmed navigation routes, ensures immediate response to medical emergencies, law enforcement and military adjustments. Tactical stealth mode uses external power sources for silent startup and covert operations. Rapid deployment configuration: some units keep engines idling for instant launch, offshore transport and high-altitude operations. Air density adjustments: BADIC compensates for lower oxygen levels at high altitudes. Enhanced cooling mechanisms ensures engine stability in hot climates. 7. Advanced safety systems during startup. The H145 startup system integrates multiple safety redundancies: automatic hot start prevention. If temperatures exceed safe limits, BADIC aborts startup automatically. Emergency engine shutdown protocols: manual overrides allow immediate engine shutdown in critical situations. Redundant hydraulic systems ensures control functionality in case of primary system failure. These safety features protect the aircraft and crew during startup operations. 8. Pre-takeoff final system checks. Before takeoff, the pilot performs weight and balance verification, ensuring proper load distribution. Hover check, confirming engine to work levels and stability. Flight plan confirmation, ensuring correct GPS and navigation settings. These final checks validate aircraft readiness before transitioning to forward flight. 9. The future of helicopter startup technology. The next generation innovations in helicopter startups include eye-assisted pre-flight diagnostics, predictive maintenance alerts before failures occur, hybrid electric propulsion, reducing fuel dependency and emissions, remote and autonomous startup capabilities, enabling remote control takeoff for unmanned operations. These advancements will redefine helicopter startup procedures, making them faster, safer, and more efficient. 10. Conclusion at the Airbus H145 Startup Excellence. The Airbus H145 startup sequence is a benchmark in road to aircraft efficiency and safety, leveraging automated engine management, cutting-edge avionics, and mission-specific adaptability. Whether in EMS, law enforcement, military, or corporate aviation, the H145 provides one of the fastest and most reliable startup processes in modern helicopters. For YouTube content, combining cockpit footage, animated overlays, and real-world pilot insights can create a highly engaging and educational experience, making helicopter startup procedures accessible to aviation enthusiasts worldwide. The Airbus H145 is a highly advanced twin-engine helicopter known for its Helionix avionics suite, BADIC-controlled engines, and multi-mission capabilities. Whether used in emergency medical services, EMS, law enforcement, military operations, corporate transport, or offshore missions, the H145 offers one of the most efficient, automated, and safety-focused startup sequences in modern rotary wing aviation. This expanded guide will cover every aspect of the H145 startup, including 1. A step-by-step breakdown of the startup process. 2. Deep dive into avionics, BADIC, and engine control systems. 3. Environmental adaptations for cold, hot, and high-altitude operations. 4. Mission-specific startup procedures for EMS, law enforcement, and military uses. 5. Advanced safety protocols and emergency handling during startup. 6. Hydraulic, electrical, and flight control system synchronization. 7. Training requirements for pilots and ground crews. 8. Real-world use cases and case studies from various operations. 9. Troubleshooting common startup issues. 10. The future of helicopter startup automation and AI-driven diagnostics. 1. A step-by-step breakdown of the startup process. The H145 startup sequence is designed for efficiency and safety, leveraging advanced automation to reduce pilot workload and startup time. The process includes pre-flight external checks, main rotor and tail rotor inspection, checking for blade integrity and balance, landing gear and shock absorber examination, ensuring stability for takeoff, engine intake and exhaust system check, preventing foreign object damage. FUD, cockpit entry and power on sequence. Battery master switch activation. A powers up avionics and electrical systems. Linux avionics boot up. A runs automated system diagnostics. Communication systems check. A establishes contact with ATC and ground crews. Engine startup process. 1. Starter motor engages. A spins up engine compressor. N1. 2. Basic controlled fuel injection. A ensures precise ignition timing. 3. Rotor brake disengagement. A allows the main rotor to begin spinning. 4. Autopilot and flight control system activation. A optimizes stability before takeoff. Once the engines reach operational RPM, the helicopter transitions to pre-takeoff configuration. 2. Deep dive into avionics, FADEC, and engine control systems. The H145's avionics and FADEC system play a crucial role in ensuring a smooth startup. Linux avionics suite. They provides real-time system monitoring, navigation, and automated flight control functions. Full authority digital engine control, FADEC. A eliminates manual throttle control, optimizing fuel efficiency and power output. Electronic flight instrument system, EFIS. A displays critical startup data, engine temperature, fuel levels, and diagnostics. These systems significantly enhance safety and reduce human error. 3. Environmental adaptations for cold, hot, and high-altitude operations. The H145 is designed to operate in extreme conditions, requiring special startup adaptations. Cold weather startup procedures. Engine preheating system may prevent soil thickening and startup failure. Battery warm-up measures. A maintains power efficiency in sub-zero temperatures. Icing prevention checks. A ensures rotor blades are clear before startup. Hot weather startup considerations. FADEC adjustments for air density. A prevents engine overheating. Fuel system monitoring. A ensures proper fuel expansion compensation. High-altitude startup adjustments. Air density compensation. A adjusts fuel-air mixture for optimal ignition. Enhanced cooling system utilization. A prevents engine performance degradation. 4. Mission-specific startup procedures. The startup process varies based on the intended mission. Emergency medical services, EMS, rapid deployment, standby power mode. A keeps systems online for instant takeoff. Quick navigation setup. A ensures fast response to emergency locations. Law enforcement operations. Tactical stealth startup. A uses external power sources to minimize noise. Instant deployment mode. A engines remain in idle for quick launch. Military and special forces use silent startup capabilities. A reduces acoustic footprint for covert operations. Armored system checks. A ensures additional protection during combat deployments. 5. Advanced safety protocols and emergency handling during startup. The H145 features multiple safety layers, ensuring startup integrity. Automatic hot start prevention. A FADEC terminates startup if temperature limits are exceeded. Engine dual redundancy. A ensures backup functionality in case of failure. Emergency shutdown protocols. A allows pilots to abort startup instantly. 6. Hydraulic, electrical, and flight control system synchronization. Once engines are online, final checks ensure rotor synchronization. A optimizes power transfer from the engines to the main rotor. Hydraulic pressure stabilization. A ensures flight control responsiveness. Electrical load balancing. A distributes power efficiently across avionics. 7. Training requirements for pilots and ground crews. Pilots undergo extensive training to master startup procedures, including simulator-based startup drills. A enhances proficiency in emergency scenarios. Live fire drills for military pilots. A ensures readiness for combat missions. 8. Real-world use cases and case studies. Several real-world operations demonstrate the efficiency of the H145 startup process. Air ambulance services in the UK and Germany. A utilizes fast startup capabilities to reach patients in under 3 minutes. Police surveillance missions in the USA keeps engines in hot standby for rapid deployment. Military deployments in conflict zones. A uses stealth startup techniques for covert operations. 9. Troubleshooting common startup issues. Pilots may encounter startup errors, requiring troubleshooting steps. Failure to ignite, check FADEC diagnostics and fuel flow systems. Hydraulic pressure warning, ensure reservoir levels are within limits. Electrical malfunctions, use backup power and conduct avionics reset. 10. The future of helicopter startup automation and AI-driven diagnostics. Airbus is developing next-generation AI systems to enhance startup automation. Predictive maintenance AI identifies potential engine failures before they occur. Remote startup capabilities AI allows operators to control startup via ground stations. Hybrid electric engine development AI reduces fuel dependency and emissions. Final thoughts on the Airbus H145 startup process. The Airbus H145 features one of the most advanced, safe, and efficient startup processes in the rotary wing aviation industry. Its automation, mission adaptability, and future innovations make it a benchmark for helicopter operations worldwide. For YouTube content, incorporating cockpit footage, interactive animations, and expert commentary will create a highly engaging and educational experience for aviation enthusiasts. Airbus H145 startup process requires an even deeper dive into every conceivable aspect of this helicopter's startup, from the smallest technical details to the broadest operational strategies. This includes the full integration of avionics, FADEC-controlled engine management, real-world case studies, pilot training methodologies, emergency response mechanisms, environmental adaptations, and futuristic advancements in helicopter startup automation. The Airbus H145 is a twin-engine, multi-role helicopter known for its advanced Helionix avionics suite, FADEC-controlled Safran Aerial 2E engines, and the highly automated cockpit that reduces pilot workload while ensuring maximum safety. The startup process for the H145 is one of the most streamlined and efficient in modern rotor aircraft, designed to allow for rapid deployment in mission-critical situations such as emergency medical services, EMS, law enforcement, search and rescue, SAR, corporate transport, offshore operations, and military applications. A comprehensive discussion on the H145 startup sequence extends beyond the standard checklist and examines the underlying technologies, environmental adaptations, training protocols, troubleshooting measures, and real-world implementations. Understanding this process is essential for pilots, maintenance crews, engineers, and aviation enthusiasts who seek a deeper appreciation for this state-of-the-art helicopter. The startup process begins before the pilot even enters the aircraft, with external pre-flight inspections that ensure the airframe, rotors, and key systems are in optimal condition. This includes an examination of the main rotor blades, tail rotor, fenestron system, landing gear integrity, engine intake and exhaust systems, and hydraulic lines. Each of these components must be in proper working order to ensure a safe and efficient startup sequence. The fenestron tail rotor system, unique to Airbus helicopters, provides enhanced safety and noise reduction while requiring precise pre-flight checks to confirm that no obstructions or structural issues could affect yaw control. The main rotor system, now featuring 5 composite blades, is designed for reduced vibration, improved aerodynamics, and increased lift efficiency. Once the external checks are complete, the pilot enters the spacious and modern cockpit, which is characterized by its glass cockpit layout, digital flight displays, and ergonomic control setup. The first step in the cockpit is to activate the battery master switch, which brings the Helionix avionics system online. This system, an Airbus innovation, features a centralized digital display that provides engine parameters, flight information, hydraulic pressures, electrical system statuses, and automatic system health checks. The startup process is significantly assisted by these digital readouts, allowing pilots to detect and resolve potential issues before initiating engine ignition. The Helionix suite performs an automated system self-check, scanning for any anomalies in the engine, flight control surfaces, communication links, and navigation systems. If all parameters are within operational limits, the startup sequence proceeds to the engine ignition phase. Unlike older helicopters that require manual throttle adjustments, the H145 is equipped with a full authority digital engine control (FADEC) system, which automatically regulates fuel flow, power output, and engine temperature during startup. This eliminates the risk of overtemping the engines, ensures a smooth and controlled ignition, and prevents common startup issues such as hot starts or compressor stalls. To initiate the first engine startup, the pilot moves the engine mode selector to start, at which point the starter motor engages and begins to spool up the N1 compressor section of the engine. As N1 speed reaches the required threshold, FADEC automatically introduces fuel, and ignition occurs in a highly controlled manner. The engine stabilizes at idle RPM, and the process is then repeated for the second engine. During this phase, pilots closely monitor engine temperature readings, torque levels, and rotor RPM. FADEC automatically prevents excessive temperature spikes, and if an abnormality is detected, it will abort the startup process to prevent damage. This is a major advancement over traditional helicopter engine management, where pilots were required to manually regulate power settings to prevent potential engine damage. Once both engines have reached stable idle conditions, the rotor brake is disengaged, allowing the 5-bladed main rotor to begin turning. This stage requires verification of hydraulic system pressures, control surface responses, and autopilot functionality. The H145 is equipped with a 4-axis autopilot, allowing for unprecedented stability in hover and cruise flight modes. Before takeoff, the autopilot is tested and engaged to ensure optimal handling characteristics. The mission-specific configuration of the helicopter at startup depends on its operational role. In EMS configurations, the helicopter is often started with standby power active, allowing medical personnel to operate onboard equipment before liftoff. In law enforcement and military applications, the startup may be conducted in stealth mode, with external power sources used to limit noise and heat signatures. Offshore transport operations require additional monitoring of engine efficiency and fuel reserves, as extended over water flights demand optimal fuel management. The pre-takeoff final system check ensures that the aircraft is fully prepared for flight. Pilots verify weight and balance considerations, navigation route programming, altitude restrictions, and fuel reserves. A hover check is performed, allowing pilots to confirm that the aircraft is responding correctly to control inputs before transitioning into forward flight. One of the most critical aspects of helicopter startup procedures is troubleshooting and emergency handling. Despite the advanced automation of the H145's FADEC and helionic systems, certain anomalies may arise during startup that require pilot intervention. Common startup issues include 1. Failure to ignite. This may be caused by fuel delivery blockages, ignition system faults, or FADEC misconfigurations. Pilots follow a standard troubleshooting checklist, including verifying fuel pump operation, electrical continuity, and FADEC reset procedures. 2. Hydraulic system warnings. If low hydraulic pressure is detected, the pilot must confirm reservoir levels, hydraulic pump functionality, and control surface responsiveness before proceeding. 3. Electrical system malfunctions. If battery voltage is insufficient or an alternator fails, the backup electrical system is engaged, and maintenance teams are alerted before further startup attempts. The future of helicopter startup automation is rapidly evolving with advancements in artificial intelligence, remote diagnostics, and hybrid electric propulsion technologies. Airbus is actively researching predictive maintenance AI, which can analyze startup data patterns and detect potential system failures before they occur. This will allow pilots and maintenance crews to preemptively address issues, reducing downtime and enhancing safety. Hybrid electric propulsion is another major area of innovation. Future iterations of the H145 may incorporate electric auxiliary power units, APUs, that allow for quieter, more efficient startup sequences. These APUs can significantly reduce fuel consumption during the startup phase while also improving overall engine longevity. Another groundbreaking development is the potential for remote and autonomous startup capabilities, which would allow ground operators to initiate startup sequences remotely before the pilot even enters the aircraft. This is particularly useful for military, search and rescue, and unmanned cargo operations, where minimizing human workload and reducing startup time is crucial. With these advancements, The startup process for helicopters like the H145 will continue to evolve, becoming even more automated, efficient, and adaptable to various operational requirements. Whether in emergency response, high-stakes law enforcement operations, or complex military engagements, the H145 startup sequence stands as a testament to Airbus's commitment to cutting-edge aviation technology and operational efficiency. For those interested in the technical and operational intricacies of rotor aircraft, the H145 remains one of the most advanced, versatile, and mission-ready helicopters in the world, making its startup process a fascinating subject for pilots, engineers, and aviation enthusiasts alike.